Start by saying that whatever I will discuss today is essentially an equilibrium problem, unlike the fracture dynamics, which is generally an out of equilibrium problem, because that happens only under the application of external forces. So, all we will do is basically standard statistical mechanics of asymmetric tether membranes. Nonetheless, the physics that we will find, or the phases that will come out of our analysis, are very unexpected and rich. So, these are my collaborators. The first two are my former PhD students. They are in Paris and Leiden, and the third one is John Toner. He is a senior professor at the University of Oregon, Eugene. So, this is the outline of my talk. So, I will spend some time in discussing the physics of symmetric tethered membranes. This is an old problem actually. So, about 25 to 30 years old and has been studied quite extensively. So, I will first discuss the elastic energy, the statistics of the flat phase, and some crumpling, and this is not really well understood yet. The second part will basically be our work, and that will be on asymmetric tethered membranes. So, we will start with the energy contributions. Then there are there is a spiral phase, which is a very novel kind of ground state for this kind of systems. The spiral state at t equal to 0. The form of the spiral is the spiral of Archimedes. Then there is also a spiral state at finite temperature, which we call new spiral, in the sense that its mathematical form has not been used in any to describe any physical system so far, at least to our knowledge. And then the last part, which is probably the most novel part of the work, which is the asymmetry induced crumpling of a membrane. Now, all these, both this old work on symmetric tethered membranes and whatever I am going to discuss in this section, use basically a Landau-Ginzburg approach, and essentially is an elastic theory. So, we will not worry about the microscopic details of the membranes, rather use a coarse grain approach where the microscopic details are all washed out and effective coarse grain degrees of freedom are used to describe to build the model. Oops. So, what are tethered membranes? So, tethered membranes are essentially two-dimensional crystals which can have undulation modes, that is, they can wiggle like this in the third direction. Out of plane distortions are allowed or are possible in these membranes. So, you can say that these are two-dimensional crystals with some degree of softness. So, as with crystals, in principle yes, but if you have disorder, then in principle yes, the tethered membrane does not require crystallinity as well as such. The problem is, if you have disorder, then to extract physics, you also have to average over disorder. That is what I am not doing. So, it is considered a pure system. So, as with crystals, you have this is essentially
disorder here also. It is just a kind of a triangulation of
I am sorry.
No, is there disorder over this lattice structure?
Yeah, sure. So, the problem is, then you need to average over the disorder to calculate everything. Yeah. So, which is what I will not be doing. So, I will basically be concerned with a pure system without any disorder. So, these are membranes with fixed connectivity. So, the neighbors do not change with time. They can distort, the structure can distort, but there is no change in the neighbors. It is a representative figure, of course. I am a theorist. It's a graphene. Graphene is a fantastic example of a tethered membrane. I mean, although this picture is a cartoon, but in reality graphene is an example of a tethered membrane. Finite temperature properties of graphene are described by the statistical mechanics of tethered membranes. So, example is a freestanding graphene sheets at finite temperature. So, the point is, the two sides of these membranes are assumed to be identical in all the studies that were done many years ago and decades ago, assume the two sides are identical. So, these are symmetric under inversion. So, these are inversion symmetric membranes. So, as with crystals, these membranes have finite in plane shear modulus, which is a very important thing, unlike lipid membranes. So, these are little technical details about how you describe the configuration of a membrane. So, you have a nearly flat patch of a membrane and then you describe it by a height function, single valued height function with respect to some base plane. The base plane is chosen completely arbitrarily. The position of a membrane is essentially is basically the radius vector r is basically given by this is the height function plus some in plane distortion u. So, not only it can go up and down, it can also move laterally. So, these membranes, the physics of these membranes are associated with two types of curvature. One is the mean curvature. So, we are discussing two dimensional systems. So, there are the curvature tensor is a 2 by 2 matrix. So, the trace of the curvature matrix is the mean curvature, which in the Morse gauge is basically del square h plus small correction order h cube, which we all neglect because we assume it to be nearly flat. So, order h cube is much smaller. Then you have the Gaussian curvature, which is the determinant of the curvature matrix, which takes a slightly more complicated form, which is quadratic in h. Oops. So, the symmetric membranes, the configuration energy comes from the in plane distortion, which are basically shear and compression. You can shear by keeping the area unchanged, you can also compress or dilate, and also out of plane undulation. So, membrane can wiggle like this. All these modes cost energy. So, t equal to 0 is a flat phase, which is not surprising because every distortion costs a positive energy. So, at t equal to 0 there should be no distortion, and so the flat state is the ground state of the system. The surprising fact is that the finite temperature state is still a flat phase until and unless the temperature is raised to a very high degree. So, there is a finite temperature flat phase, which is a surprising piece of physics coming for the symmetric membranes. And then there is a possibility of crumpling for very high temperature. These are all analyzed through renormalization group, which I am not going to discuss immediately, we will come only at the end of the talk. So, what is a shear? So, you have this, this is a cartoon of a shear. So, you have a rectangle, then you shear it, it takes this part distorted form. This is the magnitude of the shear. So, the in plane shear energy takes this form, which is which comes with the elastic modulus called the shear modulus. The symmetric tensor has this particular form. You have this usual part, which is the symmetric part of symmetrized derivative of the distortions, and then an extra part which depends on the undulation mode. The reason that it comes is because if there is a vertical displacement, that necessarily creates an in plane motion as well, either it comes closer or goes away. So, every vertical every undulation mode will necessarily create an in plane distortion. So, this is a reflection of that. Yes.
So, when you consider that like vertical displacement is possible, do you need to consider any Gaussian operation?
No, you basically assume that the thickness is not changing. It is only in that limit. So, this is a compression, the cartoon picture of a compression. Did you have a bigger square, then you compress it to a smaller square, or vice versa, smaller square and you can expand it to a bigger square. These are also cost energy, comes with another elastic constant lambda. So, this UII, which is basically the trace of the symmetric strain tensor, essentially gives a local compression or dilation. The third energy is basically the bending energy. Energy depends on the mean radius of curvature, must be even in R because of the up down symmetry. So, whether it is whether it is bent this way or bent that way, that does not matter, because there is no distinction between up and down. So, the only way you can ensure that is by claiming that the energy dependence on these modes must be even in R.
So, in your picture, metric is changing, or the metric is not changing. Means your bond distances they are changing, or they are not changing.
Bond distance will change, of course.
Bond distance.
Bond distance, that is sorry.
Bond distances are changing.
Yeah, but bond distance, the information of all those, I mean, there is no bond in this description as well.
The local metric is changing.
Local metric will definitely change. Yeah. So, this is the expression of the bending energy to the lowest order in fluctuations. It is basically the curvature square. The associated elastic modulus is the bending modulus. Now, so if of course, you can then put in all these and then write a fairly long Landau-Ginzburg kind of free energy. You can integrate out the in-plane distortion mode to write down an effective free energy that depends only on the undulation mode. So, you have this bending energy part that will always be there with or without any in-plane distortion, and then just because you are integrating out the in-plane distortions, you generate an extra piece. Now, notice that how does it come from? Where does it come from? So, you have this extra piece here, and the energy associated with the in-plane distortions are essentially quadratic in the Uij. So, that gives you a quartic piece in H. So, if you do the algebra correctly, then it takes this form, and remember that each of S, which is the Gaussian curvature, is quadratic in H. So, this part is essentially altogether overall is quartic in H. But that is just algebra. The most important part is that there is a kernel which is essentially an interaction potential between Gaussian curvatures at different points, and that is very long range, that is r square log r. So, that kind of grows as the distance between the 2 points grow, and this means you have effective long range interaction present in the system that takes this a tethered membrane outside the jurisdiction of the Marmin-Wagner theorem. Now, why do I emphasize on this point? Is because the Marmin-Wagner theorem rules out the possibility of a flat phase of a membrane in 2 dimension. The flat phase is an ordered phase. You cannot have a flat phase in 2 dimension thanks to the Marmin-Wagner theorem, but Marmin-Wagner theorem applies only if the interactions are short range. Here we show that the effective interactions are actually long range, in fact, they are very long range. So, that means we are not under any obligation to satisfy the Marmin-Wagner theorem. So, the game is open. There is a possibility of a long range, a possibility of a flat phase. So, this is basically, as I said, the t equal to 0 state is basically u equal to 0, h equal to 0, which is flat. T equal to t greater than 0 state is still flat, and we will see heuristically why it is so. So, schematically, so this is one of the distortions. So, in equilibrium, so the average of this is roughly h by L square, that gives you a bending energy of this form, kappa h square by L square, magnitude wise or scaling wise. So, that gives, if you apply equipartition theorem, is something like this. It should be of the order of kBt because we are all in equilibrium. Then the h typical, the typical value of the undulation, up down fluctuations scales as L, which means h typical by L is a constant. So, the bigger the membrane, the larger is its undulation mode. So, there is no hope of a flat phase. So, as I reach the thermodynamic limit for a membrane, the typical size of the fluctuations will also basically diverge. So, that is not a good example of a flat phase, that is not a flat. So, this is precisely this is what happens for a lipid membrane, which does not, an arbitrarily large lipid or fluid membrane does not stay in a flat phase at finite temperature, and the basic reason is essentially this. It is slightly more complicated, and there are nonlinear effects which does not actually save you for lipid membranes, it makes it worse, but this is the essential physics. Now, why is it inoperative for a tethered membrane? Now, because of the quartic interaction, there is anomalous elasticity for tethered membranes. I will not show you how it comes, that is just a standard calculation. That basically says the effective bend modulus depends on the size of the membrane. It scales as L to the power eta, where L is positive. for very large L, which means in the thermodynamic limit the bend modulus is actually infinitely large. Now, eta there is a prediction for eta which is about 0.821. I do not know how good it is numerically, but it is certainly a positive number that can be argued. So,
what does it mean physically if I get a very big membrane, very difficult to bend it?
yeah.
Is this what?
Yeah. It is easy to bend it locally, but to create a large undulation is very difficult. You can make small ripples because there the kappa effective is small, but create a large ripple is very difficult. This is what is this. Yeah, because of this.
But it's isometric. A cylinder, part of a cylinder and a sheet is isometric.
What does that go to do that? I am talking about thermal fluctuations.
Yeah.
So
I'm just trying to find out, intuitively, if I have a very long sheet and I just start to bend it at the ends, and you're saying that it's difficult to do.
first of all, you cannot make a cylinder because its spontaneous curvature is 0. We are talking about a system which has 0 spontaneous curvature. So cylinder is never a preferred state. A plane is a preferred state. The question is whether thermal fluctuations will destroy the plane or not. Cylinder is out of question. Cylinder is out of question. The question is whether you can create big ripples or not. What is the cost for creating big ripples? If kappa becomes large, as the membrane becomes bigger, the cost to create big ripples also becomes very large. That is the point. It's a statement of thermodynamics, not a statement of geometry.
Sorry,
Yes.
one naive question. So why a lipid membrane behaves like this?
Because it has no, because it has, lipid membrane behaves like this is because of this. The question that you should ask is why tethered membrane does not behave like this? Because this picture applies to tethered membrane as well.
Yeah, but why your one has this K of L and this has not the dependence with L? Why your membranes have the dependence of K depending on L and this?
For lipid membranes, they do not depend on L. For tethered, they do.
But there is a naive explanation for that or not?
Yes, it comes from here. It comes from the long.
In the lipid, this does not apply?
No, because these coefficients scale with the shear moduli. The shear moduli are 0 for lipid membrane. So this interaction disappears. This A,
This is like a
this fact, it's a fluid. A lipid membrane is just a fluid. It's a layer of fluid. A fluid doesn't have shear moduli.
and you use no more solid.
Exactly. Exactly. This A, this factor of A, it scales with the shear moduli. So from using this, the derivation of this is fairly complicated, but you can use this fact to calculate what is H typical from this figure by using this, except that in place of kappa, now use kappa of L. That gives you this. H typical scales as essentially like square root of L, which means H typical by L will vanish as L goes to infinity, which means if you take a very large membrane, the relative fluctuation will essentially vanish. So it will basically stay flat. So a large graphene sheet can stay flat, but a layer of lipid cannot because it has no shear modulus. Now, of course, crumpling, very little is known about it. The idea is that flat phase must disappear at sufficiently high temperature, because if you are at sufficiently high temperature, any order must be lost. So, 2-dimensional flat phase is a kind of ordered state that cannot survive if you go to a very high temperature at very high temperature. Unfortunately, until now there is no well accepted theory for this. This flat phase has been well studied the last 30 years. Nelson, Lubensky, Toner are probably the 3 very well known people who contributed a lot in doing all the RG and the related stuff for the flat phase. So, we will now discuss the asymmetric tethered membranes. So, many tethered membranes actually have two sides very different. For example, the red blood cells. If you take an extract of a red blood cell, the fact that it is a tethered membrane because there is an elastic spectrin network that is attached to the lipid membrane, which gives it a degree of rigidity, but it is attached only to one side. So, the two sides are different. So, which means it is an asymmetric because the top is different from the bottom. The other example is, if you take a graphene, a freestanding graphene, and then coat it with something else, for example, a layer of lipid or some polymer that makes the two sides different. It will still be a tethered membrane because the graphene will still have rigidity, but the two sides will have different. So, there will be no preference to stay flat. A flat state cannot be the ground state. That's the basic point. The fact that the flat state is not the ground state, because when you make the membrane up down asymmetric, there are extra energy terms. There is no reason for the ground state to be flat, and the extra energy terms come from spontaneous curvature. So, the membrane will try to bend like this or bend upward. See, as you change the sign of C, the membrane will flip from up to down or down to up. So, the spontaneous curvature energy has this particular form. It's just a single power of h. However, this coefficient, which is the spontaneous curvature coefficient, that can depend on the local compression, because you can imagine if there is a network attached to it that can help or prevent the local tendency to buckle, to go one way or the other. So, you can expand this coefficient assuming small in-plane distortion in this form. This chi is some thermodynamic coefficient which you need to fix the dimensions. Then the full energy functional, full Landau-Gisbach energy functional takes this particular form. You have the old bending term. These two are the elastic term that will be there in a two-dimensional system are also there for a symmetric membrane. Then the last two terms are asymmetric terms. You can see that they come with single power of h. So, if I make h2 minus h, these three terms do not change sign, but these two terms do. So, they break a symmetry that was preserved in the earlier studies. The question is, what does this symmetry breaking do? I mean, conventionally, our standard wisdom in physics says if you break a symmetry, usually that is manifested in new physics. The question is whether that wisdom is true here or not. So, again the way to study is to integrate the U modes. Now, this integration of the U modes here as well as for a symmetric membrane can actually be done exactly, because it is a Gaussian integral for U. So, if you do that, a slightly more complicated free energy comes. These two terms, the bending term and this long range term, exist even for symmetric membranes. You get two new terms. This term anyway was there for an asymmetric membrane. You get an additional term, additional long range term, which is an interaction between the mean curvature, which is del square h, and the Gaussian curvature, which is S of r. These are not local interactions, these are separated. So, the kernel is again long range, it grows as log r in 2 dimension. So, it will grow as r becomes larger, the interaction grows. Now, of course, this is not as long range as this one, but still long range. So, you expect the new physics will come out. Lastly, this effect, the bending modulus that you get out of this integration business is no longer a positive definite number, a positive definite coefficient. The bend modulus for stability reason should be positive, otherwise spontaneous bending will be favored. But in this case, actually that is possible. By choosing this thermodynamic coefficient, you can make the bend modulus here to be negative. We will try to understand the consequence of a negative bending modulus towards the end of the talk. So, what is the ground state? So, there are two possibilities in the ground state at t equal to 0. It will be, claim is that it will be in a spiral state or it will be crumpled already at t equal to 0. Remember, for symmetric membranes, the crumpling due to crumpling can occur only at high temperature, because that is the way you can maximize entropy. Here, the crumpling can occur already at t equal to 0. So, let us first assume that bend modulus is positive, which is the simpler case. So, there will still be a competition between these two facts, that in plane elasticity does not want Gaussian curvature, because this is a long range term. if you create a global Gaussian curvature, that costs a lot of energy through this. So, the in-plane elasticity, which is responsible for creation of these long range terms, do not like Gaussian curvatures, which means a Gaussian curvature will be there only if you bend it in two different directions, otherwise Gaussian curvature is 0. So, the in-plane elasticity favors Gaussian curvature to be 0, but it does want the mean curvature to be non-zero, because to start with we have a spontaneous curvature. So, there are two competing interests. You can achieve, surprisingly, you can achieve both by bending in one direction. If you bend only in one direction and remain flat in the other direction, automatically the Gaussian curvature is 0, but since you are bending in one direction, you pick up a spontaneous curvature. So, that you kind of satisfies both the requirements. Now, of course, you can minimize energy to find the optimal radius, that is the preferred radius of curvature. The membrane tries to roll up into a cylinder of radius r naught at t equal to 0, but this is not all. The problem is, if the membrane size is much bigger than r naught, then it cannot roll into a cylinder of radius r naught, because it will not simply fit in. Well, there will be a lot of extra part remaining after creating a cylinder of size r naught. So, the best compromise, basically it cannot roll into a cylinder of r naught because of excluded volume. When you roll, you come back to the same point, and then you cannot re-roll on the same arc, because there is already a piece of membrane there. You have to go outside. So, basically start mismatching the radius of curvature. So, the best compromise is a double spiral. Okay, so why double spiral? The double spiral, because you start rolling, do you have a piece of paper, Pinaki? I'll use this. So, membrane basically starts rolling like this. So, let us say it makes one roll, which sort of fits into the radius of curvature, but still a huge part is remaining. So, it can start rolling, roll until it gets completely exhausted. But you can easily see the inner layer satisfies this R naught condition. So, that the inner layer is in the minimum free energy condition or minimum energy configuration, because we are at t equal to 0. But as you keep going outside, keep taking the outer and outer layers, you are no longer satisfying the minimum energy configuration. You are basically gaining more and more energy. By the time you come to the outermost layer, you have actually gained a lot of energy, because the mismatch is quite large. You can minimize the mismatch by rolling, start rolling from two different directions, something like this. Then you can easily convince yourself the amount of mismatch in the two cylinders, in the two spirals, is actually lower than the amount of mismatch that you would accrue if you roll into just one spiral. So, a double spiral has a lower energy than a single spiral. So, a double spiral has is a preferred ground state for this system. Now, you can minimize energy and find out the form of the equation of the double spiral. Essentially, r is proportional to theta. This is called the spiral of Archimedes. So, total radius r essentially grows as square root of L. If kappa is 0, that will happen if the thermodynamic coefficient chi is quite large. Then of course, if the bending modulus is negative, energetically it is favorable to create a lot of bending, and that essentially the membrane gets crumpled at t equal to 0. So, t equal to 0 picture is fairly simple. So, this is a stability diagram, bend modulus versus the thermodynamic coefficient. So, there is a stable phase where the membrane is spiral, there are unstable parts where the membrane gets completely crumpled. Remember, these are all at t equal to 0. This is thermal fluctuation plays no role here. That is equal to t greater than 0 state. This is more complicated as well as more interesting. So, you can easily imagine that if I roll a membrane like this, let me roll it into one because it is easier to roll. Then if I if it's a huge, if there are a lot of turns, then if I cut a small portion, it will basically look basically parallel sheets So, that basically looks like a stack of membrane. Just by looking at a small piece, a small segment of a cut, you will not know whether it comes from a spiral or just infinitely long, stack of, parallel membranes. So, now at t equal to 0, of course, the stack is essentially static. There is nothing which will make the members of the stack to fluctuate. But as soon as you raise the temperature, the individual members of the stack will basically start to wiggle like this, then basically touch occasionally here and here. They will basically hit each other at some typical distances. Because of this random hits, which are essentially due to the thermal fluctuation, the layers, the individual members or the stack will try to expand. So, essentially thermal fluctuation creates an effective repulsive interaction in a stack, which is called the Helfrich interaction. Now, of course, they do not really keep touching at very small distances. If the temperature is low, they will touch at fairly large distances. So, there is a typical length scale L sub h called Helfrich length, named after the German scientist Helfrich, who first thought of this physics. If the length scale that you are probing is much smaller than the Helfrich length, then the individual segment does not know that there are other segments around, because it knows the existence of other segments only by hitting. If the typical hits are between distances or over a scale of LH, then segments smaller than LH will not know that there are other segments. So, they are isolated. So, the physics of an isolated membrane can be applied to segments which are smaller than L sub h. So, as I said, for L much smaller than L sub h, the membrane segments look flat because they are too small and isolated. So, for these regions, self avoidance and spontaneous curvature can be ignored because they are almost flat, and self avoidance, the question of self avoidance comes only if they come close to each other. If they are not touching each other, there is no hassle over self avoidance. So, the standard analysis for an isolated membrane in terms of Morse gauge works perfectly. So, you can apply the standard denormalization group method, which I will not describe, to extract the physics valid within scales smaller than LH. So, there are two, as is common in RG, there are two coupling constants that determine the physics. This is what that exists even for a symmetric membrane. This is what we find for an asymmetric membrane. So, this is the phase space in the coupling constant space. There is a spatial line which I call separatrix. I will tell you what that means. So, the lower part, in this part, there is a fixed point which I mark as ALFP, named after Aronowitz and Lubensky, who first did the analysis for a symmetric membrane. So, the RG flow lines converge to the ALFP fixed point for symmetric membrane. So, if you are in this region, your physics within the scale LH is identical to the physics of symmetric tethered membrane, which was discussed 20 years ago, 25 years ago. So, this is the essence of this part. So, this is a spatial line, as I said. If you flow along this line, you just keep flowing, you do not go anywhere, you neither come here, you nor go there. So, this separatrix by definition separates the two parts of a phase diagram. If you are here, something
What is this A and B?
It's basically, I will show you.
These two coupling constants,
I will show you what A and B.
same, one is
A and B are here. So, A is what? A is essentially the amplitude of the long range interaction for a symmetric membrane, and B is the extra long range interaction that you get in the asymmetric case. Both of them scale with B basically scales with the asymmetry parameter, and A scales with the elastic modulus, the in plane elastic moduli. So, basically they determine the scale of the effective interactions.
because G1 by G2 is A by B times kappa. If
Sure. Yeah. So that's an interpretation of this. If you flow along, this is the line along which G1 by G2 is actually fixed. So basically, along this line, there is no change. There is basically there is no renormalization of the bend modulus, which is what you are basically saying. On this side, kappa grows bigger and bigger, and the system is described by what Aronowitz and Lubinsky told us decades ago. On the other side, something else happens, so that I will come at a later stage. Let us first analyze the physics on this side. Yes?
For the symmetric membrane, you are only on the horizontal axis and
exactly.
You have the transition, sort of transition there.
Okay, this is a very good point. If you are a symmetric membrane, you are only on this axis. So there are two arrows. So apparently there is a transition. So it is believed that there is another fixed point which controls the crumpling transition, whose existence is only speculated upon. But if there is a crumpled phase, there should be another fixed point. So if there is another fixed point which is unstable because it is a phase transition, you expect there is a flow away from that. This controls the flat phase, and beyond that speculated fixed point you have the crumpled phase, which you do not know how it looks like. So this arrow is somewhat speculative, I agree. So for if you are on the this side, the ALFP side, you essentially have local lamellar, sorry, there is a typo, phases of symmetric membranes. This you can show that this Helfrich length basically scales with H typical. You can use standard scaling argument, and it scales with some exponent. This exponent eta is what appears in the renormalization of the bend modulus for symmetric membrane. And then you assume that each this is the basic idea of the Helfrich energy, that each contact costs free energy of the order of kBt. So the free energy of contacts per area has this particular form. Now you have this extra energy in the lamellar phase, and then you balance it against a spontaneous curvature and minimize the free energy. Now why do you balance the spontaneous curvature? Because the spontaneous curvature tries to keep it in a rolled shape. That is what it does, spontaneous curvature. The Helfrich repulsion tries to open up the spiral because it is repelled, so it swells up. So there is a competition, somewhere they balance, and wherever they balance, that's your state basically. So basically balance these two and minimize the free energy. After some algebra, you basically get yet another spiral with an exponent which is about 1.42, which is larger than 1, which is what it should be, because it is a swelled up spiral. It is a spiral which we did not find in physics before. So it is still a double spiral. It will be double for the same reason as it is a double spiral at t equal to 0, but it is a swelled up double spiral. It will look much bigger. So the crumpling, if you are above the separatrix, that is if you are on this side, then what is your fate? The RG flow lines rapidly flow to infinity. So they all go to infinity. So you can show, and I will show in the next slide, that perturbative corrections to the bend modulus due to the long range interactions can be positive or negative. So you have no idea whether ultimately the renormalized bend modulus will be positive or negative, which is a somewhat worrisome thing, but it basically means the scale dependent of the renormalized bend modulus can vanish as the membrane segment exceeds a particular size, or equivalently this thermodynamic, look at this picture, this thermodynamic coefficient chi exceeds the threshold exceeds the lower threshold or a crumpling length. So this means there is a possibility of finite temperature crumpling that is size dependent. So unless the size becomes large, you will not see this crumpling happening. So where does the size come from? We will now see this. So, we are basically interested in the effective bend modulus kappa e, the effective because the nonlinear interactions change the bend modulus that you measure in experiments. The change has this particular complicated form. Do not worry about the algebra, just note there is one part which is positive definite, and then there is a second part which comes with a minus sign. So, there is a competition. So, the positive definite part comes with the factor of A that exists even for a symmetric membrane. So, if this part dominates, then the effective bend modulus will be bigger than what you start with. If the second term dominates, then effective bend modulus will slowly come down. In fact, if this is too large, then this can actually vanish somewhere. And then in terms of Rg, this basically means the coupling constants becomes order 1 in finite Rg time. So, basically I mean there is no time here, time is basically a proxy for size here. So, basically within a finite size you can basically see the effective bend modulus has vanished if B is too large. So, by figuring out at what size the bending modulus actually vanishes, you can calculate a length called a persistence length, which is like a persistence length for a polymer, the length up to which a segment remains roughly flat, beyond which the flatness disappears. It has the same interpretation. That length is denoted as xi. This xi satisfies this somewhat complicated equation. There are two solutions. One, if the right hand side vanishes, then xi is 0. If xi is 0, basically means the membrane is crumpled at all scales, which is the 0 temperature crumpling I referred to, or this delta is 0. This is not 0, but this delta is 0, then basically means xi approaches infinity. So, xi can be anywhere between 0 and infinity. If xi is infinity, meaning you will basically not see crumpling until you hit infinitely large size. Xi finite, meaning there is a finite size, and as you exceed the size you will see the effect of crumpling. So, xi you actually see depends on temperature. So, as T becomes smaller and smaller, xi gets bigger and bigger because the thermal fluctuation effects become smaller and smaller, which is not surprising. Now, of course, is this all? But this is unfortunately not all. The question is, can excluded volume interactions prevent crumpling? Because you see, membrane to start with, membrane tries to be in this shape. Now, because of excluded volume, it is not a perfect cylinder, but it is a spiral. Now, if it has to crumple, it has to really fluctuate a lot. It will have a very irregular shape. To do that, there will be a lot of hits between different layers. So, basically excluded volume interaction will be important now, that the fact that the same space cannot be occupied by two different segments of the membrane, and the excluded volume interaction will try to keep the fluctuations under control, because if the inner layers have to fluctuate a lot, they have to basically go through the outer layers, basically completely destroy the outer layers. So, that is not an easy task. So, the excluded volume interaction has a property or has the nature of containing any large fluctuations. The question is, to what degree does it work? Can it prevent crumpling completely? What happened? 5 minutes? Okay. So, now you see that this is the shape. So, there is a straight part and there are two spirals. So, the straight portion here has no neighbor, these have neighbors. So, are subject to excluded volume interactions. This has no neighbor, so is not subject to any excluded volume interaction. So, can easily crumple, but then there is other issue. So, because there are two spirals like this, it tries to spontaneous curvature tries to roll very tightly. So, there is a stretch on the straight segment, creating an effective surface tension, and a surface tension is always known to stop any crumpling. If there is surface tension, there will be no crumpling. So now there will be a competition between the surface tension and the degree of and the tendency to crumpling. You can figure out a length by balancing the surface tension and the bend modulus, and that is a critical length. That critical length is essentially the the limiting size. If the persistence length is smaller than if this condition is satisfied, then crumpling will happen, because beyond L sigma it's surface tension control, there will be no crumpling. Below L sigma crumpling can happen. So if size of the membrane is smaller than is bigger than the persistence length, and the length at which surface tension becomes operative is bigger than the persistence length, the membrane will crumple. What its shape will be is very difficult to predict, that is beyond the elastic theory that we have written down. So this is the phase diagram, this is the final phase diagram actually. So there is a spiral phase, which is a nice shape, we know a lot of physics about it. Then there is what we call WC, weakly crumpled phase, where the crumpling is scale dependent, and then there is an outer phase, there are two outer phases which are strongly coupled, which are always coupled even at temperature T equal to 0. These get crumpled only at finite temperature. These are the same phase diagram in a L versus chi-square plot. You have a spiral phase and there is a crumpled phase, and the phase boundary goes like this. This is a summary. There are essentially 2 points. So there is a new double spiral phase, both at T equal to 0 and T greater than 0, but the T greater than 0 phase swells up a lot. The membrane can get crumpled at T equal to 0 or at T greater than 0, and these are the references. Thank you.
So what is the real?
What is it?
I mean, real systems, what to?
That depends on, see, everything depends on the thermodynamic parameter phi. I mean, in our analysis, phi is a floating parameter, but that's a material dependent parameter. So as you change, as you use different materials, you will have different phi. So accordingly, your location will be in the phase.
But do people see such kind of structures?
What I know that in some graphing sheets, people have seen tendency to spiral, but how cleanly they find a double spiral, I am not so sure. But also see, like in real experiment, there may be other factors which are all excluded here, which might favor a single spiral problem. There will be other interactions, there will be dry, this and that. If you don't know, this is the zeroth order. Yes.
Yes.
How do the radius of the spiral, how it grows with L?
So at T equal to 0, it grows a square root of L. At T greater than 0, it grows with a power which is larger than L.
So have you considered the collision of the two rolls?
Yes. Oh, only the two rolls?
Yeah, but because the weight of the flat.
That will happen at a very, when the expansions are really large.
But then the flat part doesn't contribute at all.
No, it will still, right? Because even
But it's very small, no?
it doesn't have it will be quite substantial because the rolls are now big. The distance between
exactly,
the centers will still be substantial. Even if they hit, since the thermodynamic limit, each roll has infinite lengths.
Yeah.
In the thermodynamic limit, of course. So the distance between their centers is actually quite large, and that is the size of the straight portion.
Okay.
So, you mentioned about depletion interaction for
Helfrich.
formation of this.
Yes.
Yeah. So, if you change the depletion interaction by putting some polymers or some other additives in the solution, so can you control the what kind of structure you get when? Because this is just like the same sheet is running into each other.
Right.
That is giving the depletion. But if you have some smaller, like the conventional depletion interaction.
So, one possibility is you change the amplitude. That will not change the shape. The only thing that can do surprises if you can change the power law that is associated with the depletion interaction. That I don't know what you have to do, but that's a good question. That probably it's possible that you insert something else that changes the power. See, by changing the amplitude, you will only change probably some quantitative things, but not really the shape.